Hello, in this video I will review Chapter 1 of Kasumu's book, Introduction to Stochastic Processes. Now, what is a stochastic process? That's what we'll start with. Suppose that each performance of an experiment yields a real-valued function on an interval. The diagrams below show possible realizations where t in most cases corresponds to time and xt is the value observed at time t. Alright, so this is a graph. Here we have the value of x as a function of t. It's a real valued function, so you can have positive or negative numbers. And here's the graph of the function. It changes as t changes. These are two possible graphs. Here's a graph of another function, a step function, that takes discrete values. It's possible, for instance, that these values are 1, 2, 3, 4, etc. And it's possible that these jumps occur at times 0, 1, 2, 3, 4, and so on. So here I would say x0 equals 1 because the value of the function when t equals 0 is 1. Then x1 equals 2, x2 equals 3, and so on. Now notice here that the continuous time really does not bias anything. We only need the value of the function at time 0, time 1, time 2, and so on. Now, if the experiment is performed at times t0, t1, t2, up to tn, where the times are ordered so that t0 is less than t1, is less than t2, and so on, then these values xt0, xt1, up to xtn are random variables. So, for instance, we can give an example. Suppose I throw a dice at times. I can set one dice at time 0, and I can throw the dice again at time 1, 2, 3, And I would let xn denote the value of the dice at the nth throw. Okay. Now let me give another example. Suppose I throw a dice at same times. So I'll copy this. But in this case, I'm going to let yn denote the sum of values for the dice up to the nth throw. Now, these are actually both examples of stochastic processes, but they have very different characteristics. If you are going to graph the first one, you can imagine what a typical graph would look like. As a function of time, or a function of number of throws, so these would be 0, 1, 2, 3, 4, etc. This variable does not have to be time. In this case, it's the number of throws. So in fact, it's going to be an integer and not a real number. All right, now if I consider the first sequence, you can imagine what that would look like. The first throw could be 1, next one might be 3, next one might be 2, next one might be 4, might be 6. Right, the possible values that it's going to take are between 1 and 6, right? So I can indicate that this way. This would be 1, 2, 3, 4, 5. And for each time, I'd have one of these spots, right? And I could continue this process. But the process would always remain between 1 and 6. So here we keep going here, always between 1 and 6. So that would be one particular example of x sub n. And you could call that a sample path. It's important to understand that random variables do not take fixed values. Random variable is something that can be different. If you want to think of a random variable, you need to think of all possible values and the probabilities of those values. So similarly, if you want to think of a stochastic process, you need to think of all possible values of all of the random variables in the sequence. So there are many, many different instances, many examples. Some look like, one might look like this, another one might look very differently. Now let's look at yn. What's going to happen with yn? Well, the difference between xn and yn is that yn will always be increasing. Yn might start out at 3, say. If the second throw is 2, it would go up to 5. If the third throw was 6, it would go all the way up to 11, and so on. So this would be a sample path for yn. And it's just one sample path, just one example. In this case, yn is increasing. Yn will always be increasing. So different stochastic processes may have very different characteristics. All right, so let's go back here again. If the experiment is performed at time t0, t1 up to tn, then xt0, xt1, xtn are random variables. Think about throwing a dice. Each time you throw the dice, that's one random variable. And x5 would be the dice result on the fifth roll. Thus, we can define a stochastic process as a collection of random variables defined on the same probability space. Each xt is a function xt from omega to r. Now, what is this mysterious omega here? Omega is the set of possible outcomes of an experiment. For instance, when you throw a dice, the outcome is how the dice lands. From how the dice lands, you read the number on the top of the dice. So I'll write that on the side here. Now mathematically, you can conceive of omega as the interval 0, 1, where in practice you choose a number between 0 and 1 randomly. In fact, when you generate random numbers on the computer, they all come from this simple random function that generates a random number between 0 and 1. Similarly, you can imagine associating with some throw of the dice a random number from 0 to 1. In this case, the throw of one dice, we can think of that as the following function. From 0 to 1, we can divide this into 6 equal intervals. The possible values would be 1 to 6. So from 0 to 1 over 6, we could take the value 1. From 1 over 6 to 2 over 6, we take the value 2. From 2 over 6 to 3 over 6, we take the value 3. And so on. So if you chose a random number in the interval from 0 to 1, then this random variable x would take the values 1, 2, 3, 4, 5, 6 with the right probabilities. So I'll just write that here. And choose a random number in 0, 1. Then the outcome mimics the outcome of the throw of a dice. So I can say that mathematically this gives me the result of the throw of a dice for all practical purposes. Okay, so we've introduced the basic idea of stochastic process, and we'll continue in the next video.